Prannoy, I introduced him. He is a professor at the University of Miami. We are very proud that he has been our alumnus. He did his BTech with us, and we are very certainly proud of it. And after that, he's been traveling the whole world. From Chennai, he went to Urbana-Champaign in the Midwest of the United States. Then he went to Switzerland. Then he came back. He did a postdoc at Oregon State University. Now he's an assistant professor at the University of Miami.
Thank you, Professor Gettu, for the kind introduction, and thank you all for giving me the opportunity to present at this workshop. My name is Prannoy Suraneni, and I will be talking about rapid screening tests for supplementary cementitious materials. So I want to start off with a short introduction about supplementary cementitious materials. Many also know them as mineral admixtures. These are finely ground calcium aluminosilicates, which are often the byproduct or waste from various industrial processes. Examples include fly ash, slag, metakaolin, silica fume, which are shown in this picture on the right. Now, most current concrete contains some supplementary cementitious materials, which I assume there's no problem. If there is, please interrupt me. There's just some chat coming, but I don't think that's an issue. Anyway, most current concrete contains quite a bit of supplementary cementitious materials, and that replaces the cement. So the reason for using supplementary cementitious materials is that they provide very significant benefits to concrete. And these benefits range from reductions in CO2 impacts. And that's a big thing because cement has a very high CO2 impact, and using these SCMs reduces that CO2 impact. SCMs also improve fresh properties and later age strength, but most importantly, they improve concrete durability, which is a major reason for the use. They also reduce cost in some cases. Now, when we consider availability and usage of supplementary cementitious materials, there are a lot of supplementary cementitious materials that are available in very large volumes, but the ones that we use most often and most commonly are fly ash, blast furnace slag, and silica fume. And if you look here, these are actually available in relatively small quantities. And in the current situation, there are a lot of coal-fired power plants which are being shut down. Because of this shutdown, increasing shortages of fly ash and also slags are being reported locally. So this necessitates that new supplementary cementitious materials have to be identified and characterized. And there are a lot of these new supplementary cementitious materials, novel materials, alternative materials, you can call them all of that, calcined clays, natural pozzolans, reclaimed fly ashes, steel slags, etc. And if you look here in terms of volumes, you can see that some of these are available in very, very, very large quantities. So what is needed then is we need to understand how these things behave and identify what are valuable new SCMs. Now, what are the different types of SCMs? Technically, you have two different types of SCMs. The first is pozzolanic, and the second is latent hydraulic. The difference between these two is that pozzolanic SCMs react with calcium hydroxide and water at high pH to form CSH. On the other hand, latent hydraulic SCMs do not need calcium hydroxide, which is also referred to as CH here and in other texts. They do not need CH. They can simply react with water once they are activated to form CSH. Differently from pozzolanic and latent hydraulic SCMs, inert fillers are materials which do not react with water or with calcium hydroxide. They can show other reactions which are a bit out of the scope of this presentation. I won't discuss them, but limestone is a very good example for a inert filler. Now, it is absolutely critical to differentiate pozzolanic, latent hydraulic, and inert materials. So there are two reasons for that. The first is that these are used at different replacement levels in concrete. For example, a pozzolanic material, you use it at maybe 20-25%. Latent hydraulic, you can use it up to 40%, and inert, you can use it up to 15%. So it's important to know when you have a random material what it is. And also, these different materials have very different benefits for concrete durability. I won't get into the details for this graph, but basically it shows that when you have alkali activated reaction, different amount of fly ash versus different amount of slag is beneficial. So then the question is, how, when you're given an unknown powder, do you say this is pozzolanic, this is latent hydraulic, or it's inert? Can we just look at the chemical composition of that SCM and make that distinction? And if you look at this figure here, it kind of looks like pozzolanic, latent hydraulic, and inert materials have somewhat different chemical compositions. I would like to warn you that this is not true. Simply using SCM chemistry does not work, okay? And a very simple analysis of something like a silica fume, which is a very reactive and pozzolanic material, versus quartz, which is a completely inert material, makes that clear, because both of these are typically very high in SiO2. They're about 95% SiO2, okay? But obviously they behave in a very different manner. So you cannot use simple bulk amorphous content. And the reason for that is because the reactivity actually depends on the amorphous amounts of CaO, SiO2, and Al2O3. The problem is these are quite complicated to determine. So it's not as easy as just determining the bulk composition, for example. Now, in the US, one of the ways that SCMs are screened when it comes to US fly ash specifications, for example, is, and the specification is ASTM C618, by the way, but the test is known as a strength activity index test. So what that test does is it checks whether a 20% replacement with fly ash attains a fixed strength level. It's 75% of the control mix without any fly ash. So if you replace with 20% SCM and the strength reduction is less than 25%, the test is like, okay, you have a reactive material. Unfortunately, this test does not work. Many inert fillers also pass this test. And I will not get into the details, but basically what's happening is the replacement level, which is 20%, and the limits are both likely too low, okay? So there isn't much value in using this, although people still do. Now, let's think of first principles in trying to design an SCM screening test. Basically, what is happening is as follows. The SCM is reacting with calcium hydroxide and water at high pH to form CSH, calcium silicate hydrate. Now, as the reaction proceeds, what is happening is that the SCM dissolves into the solution. This dissolution and the subsequent reaction releases heat. The reaction consumes calcium hydroxide, and when the hydrate products are formed, they bind some water together. And as this forms a solid structure, you can get strength. So all of these are things that can be measured, and they are indicators of extent of reaction of SCMs. So all of these can technically be used to screen for SCM reactivity or to screen SCMs from inert materials. Now, this is just a model system that I drew, but you can vary it. You can have cement or you don't have to have cement. You can also vary mixture proportions however you want. You can change the alkaline solution composition. You can change temperature. You can change pH. So this can be changed in a very significant manner, but to a certain extent, to a certain extent. It doesn't matter so much because essentially you're measuring these various things. So the way you screen is basically you say if all of these meet some kind of a certain threshold, then the material is an SCM. Otherwise, it is not. Now, there are many tests that measure all of these. So the heat release is measured in what is known as R3 and modified R3 tests. The R3 stands for rapid, robust, and reliable. Reproducible has also been used, and I'll explain what that is. There's also a modified version. Bound water is also measured by these tests. Calcium hydroxide consumption is measured by Chappell, Frettini. You can do thermogravimetric analysis on cement SCM systems. For strength, there's a lime strength test, a strength activity index test, several other tests. And there is a very good paper from Snellings and Scrivener, which discusses all of these in a significant amount of detail, and you should check it out if you're interested. Now, the rest of this talk is going to focus on recent advances, which is the title of this workshop, right? So I'm only going to talk about what has happened in the last 7 years or so, okay? So in that time frame, there's been very significant research and progress on the R3 test, the modified R3 test, and the lime strength test. And Professor Gettu mentioned RILEM. A lot of research on this has been led by RILEM, specifically TC267TRM. Some work has also been done at ASTM, CO9.24. And if we think about what a screening test should do, ideally, a screening test should differentiate inert and reactive SCMs. It should differentiate inert, pozzolanic, and latent hydraulic SCMs. It should be able to predict the compressive strength development in concrete. And it should predict some aspects of concrete durability. Now, none of the tests do all of these. Several of them do some of them. And there's a lot of research ongoing, for example, in linking SCM reactivity to concrete durability. So all of these parameters can be done, but you probably don't have a one-size-fits-all approach in terms of test development. Now, to use a test in specifications, such as the specification for fly ash, in addition to all of this, it must also be simple and cheap. So let's talk a little bit about the R3 test. Essentially, what you're doing in the R3 test, you have a model system. It has potassium hydroxide. It has a bunch of other things. There's different types of R3. In the modified R3, it's just this. The original R3 has a couple of other things. But regardless, it's SCM, high alkali solution, calcium hydroxide. You mix them, and then you put them in an isothermal calorimeter. What this does is it measures the heat of reaction, okay? And after you're finished, you can run thermogravimetric analysis on it, using which you can measure calcium hydroxide consumption or the water that is bound by a chemical reaction. But you can also measure the bound water using simply a furnace by measuring the mass loss from about 50 degrees to 350 degrees. So there's several different ways of doing it. But ultimately, in the R3 test, heat release or bound water are measured. In the modified R3 test, heat release is measured, and so is calcium hydroxide consumption. And instead of the heat release, you can also measure the bound water. So these are results taken from Snellings and Scrivener, and they basically show that you can very clearly differentiate a very reactive SCM, slightly reactive SCMs, and inert materials. And you see differences both in the total heat release and in the rate of heat release. More importantly, you actually see very strong correlations between the heat release or the bound water and compressive strength development, which are highlighted in these oval shapes here. In addition, the bound water that is measured correlates very nicely to the cumulative heat that is measured. And both the bound water and the cumulative heat correlate with the compressive strength. Now, There is a very significant advantage that can be exploited when you consider bound water versus cumulative heat release. To measure the cumulative heat release, you need an isothermal calorimeter, which is an equipment that costs about 30,000 US dollars. On the other hand, to measure bound water, you need a furnace, which is an equipment that costs about $3,000. So you get a 10x savings in cost. Of course, there's no such thing as a free lunch. You lose something in terms of precision, continuous measurements, etc. But it is a very attractive proposition for many to use the bound water instead. And I've listed the papers here. I can send them to you later if you send me an email as well, which give the details of this testing. The lime strength, it's basically a really, really simple test. You just measure compressive strength of a lime mortar mixture. And there's different mixtures, solutions, curing. They can all be changed. There's a similar Indian standard. There's a similar Canadian standard as well. But the way you do this test, it depends. And optimization is kind of required for this test. But the nice thing is, if you look at strengths, and this is in a lime mortar, you can see a very clear differentiation between limestone, which again, as a reminder, is an inert material and shows zero strength, versus a metakaolin, which is very reactive, shows very high strength, and fly ash, which is somewhere in between. The one concern that people have had regarding this test is it is suspected that interlab variation values can be quite high. So there might be some challenges towards standardizing this test. And the reference paper has a lot of details and very nice test results. Now, one of the nice advantages that our research group has found when looking at this test is that there is a very nice correlation between the lime strength that is measured and the properties of cement paste that result. As an example, the lime mortar compressive strength is nicely correlated with both the heat release and the calcium hydroxide consumption that is measured in cement paste. So this suggests that the lime strength is an accurate indicator of properties that develop in cement paste. It hasn't been validated for concrete, but one would hope that a similar result will hold. Now, both these tests, the lime strength and the R3, they are measures of total reactivity. They do not differentiate between pozzolanic and hydraulic reactivity. Now, what we do in my research group is that we measure both the heat release and the calcium hydroxide consumption. Now, the reason for doing that is this is a model graph, for example, which shows that you can have two materials which can have very similar calcium hydroxide consumption. For example, slag and quartz. You can also have two materials which can have very similar heat release. For example, slag and a calcine clay or a metakaolin. But a slag behaves very differently from a quartz, which behaves very differently from a calcine clay. So there is very significant merit in measuring both the heat and the calcium hydroxide consumption if you want to distinguish between pozzolanic and latent hydraulic behavior, which is in some cases very important. So we've been calling this the modified R3 test. We've tested it on about 120 SCMs so far. My PhD student Shivakumar Ramanathan has led a lot of work on this. And the graph here does not show 120 materials. It's an old graph, but basically you can see from the ovals that are drawn that there is a very clear distinction between inert materials, latent hydraulic materials, and pozzolanic materials. And you can also get an idea about less and more reactive SCMs. Specifically, as you go at a 45-degree angle, like this, you are having an increase in reactivity. And as you go in this direction or this direction, which is from right to left, the way I see my screen, you're going from pozzolanic to latent hydraulic behavior. And we actually have reasons and we can explain why all of this happens. But very simply, basically what is happening is that the latent hydraulic materials are high in calcium oxide and they don't consume a lot of calcium hydroxide, which is why they may have high heat, but they don't have high calcium hydroxide consumption. Now, the boundaries that we have are subjective at this point in time, and they're only really based on the sort of clustering that we see of the data points, but work is ongoing to improve this clustering. Now, what we have been able to do is we've drawn up boundaries based on our clustering. The boundaries are given here to separate out inert, pozzolanic less reactive, pozzolanic more reactive, latent hydraulic less reactive, and latent hydraulic more reactive materials. So if you give me any random material, it could be any material, right? You could give me a powdered glass, for example, or you can just powder up some wood and give it to me. Any material you give me, I'm going to tell you, hey, this is pozzolanic, or hey, this is inert, hey, this is hydraulic. And we've actually demonstrated this with numerous alternative SCMs, at least 30 or 40. If you remember, that was the whole point of doing this, right? We need screening tests for alternative SCMs. And we've shown, for example, that several of these materials, which include some alternative slags, which include sandstone, which include granite filler, which include limestone, these are inert, right? So these cannot be used as SCMs. We've shown several others to be pozzolanic, we've shown several others to be hydraulic, and our findings generally agree with the results of literature and other tests we've done on these materials. So steel slags, corn ashes, biomass ashes, ground glass, ground lightrate aggregates, basalt fines, fillers, municipal solid waste incineration fly ash, bottom ash, all of these are materials that we have tested in our lab. And the one thing I want to point out is that this is a screening test. It's not to say that if you measure something to be reactive, you can definitely use it in concrete. No, you have to look at other things as well. But if something is inert, you know that it's inert for sure. So you have to use it in combination with other testing, of course, but as a screening test, it seems to have tremendous potential. Now, we have also shown that the calcium hydroxide consumption that is measured has a moderate correlation with bulk calcium oxide contents and bulk silica contents. The correlation is only going to be moderate because in reality, the exact relationship likely depends on amorphous CaO, SiO2, and Al2O3 amounts. And as I mentioned, these are quite hard to measure. So this approximate relationship is still valid, but you have to use it with caution. The particle size of the SCM that you're using also has a very significant influence. And for effective comparison of different materials, we recommend using roughly the similar particle size or fineness for all these different SCMs, although in practice, we acknowledge that that's not easy. Now, let's talk about standardization and specification for just a minute. The R3 test is on its way to standardization. The lime strength test is based on an existing standard test. It should be relatively easy to standardize these. There is, at this moment, no attempt to standardize the modified R3 test. When you talk about specification is something that something like fly ash has to meet. Isothermal calorimetry and thermogravimetric analysis are too costly and too complex for use in specification. So most likely for specification, what makes most sense is bound water or calcium hydroxide consumption, but using a furnace, which, as I said, only has a capital cost of about $3,000. There are some other choices for specification. As an example, I said the strength activity index test does not work, but you can accelerate that test and you can make it more effective, better using high temperature, or you can use high replacement levels and make the test work. As far as we know, research on this has been very limited, so I'm not really covering it. Then there is bulk resistivity. Resistivity is, in very simple terms, measuring how resistant the concrete is to current passing through. And you can combine the strength activity index and the resistivity test as well. We've done a lot of work with resistivity, and think of resistivity as quality of concrete, okay? An indicator of durability. And so far, our results show that when you test with inert fillers, like limestone here, the resistivity is reduced. On the other hand, when you have reactive materials, the resistivity is increased, and very roughly, very reactive materials seem to increase the resistivity a lot. If the shape looks familiar, it's because a lot of the previous curves have had very similar shapes actually, and very roughly all of these are measuring similar things. But the resistivity has shown value as well, and we can really clearly see these differences if we use high replacement levels of SCMs or test it at later ages. So we've actually done that, and we've shown that at 60% replacement, for example, the differences in resistivity are very obvious. So with that, I would like to get to my conclusions. So basically, rapid screening tests are needed because we have a lot of alternative SCMs and we want to screen the good from the bad. They are in general based on this model system, and they analyze various measures of reaction. Okay, so quantitatively, when you have more dissolution, more heat release, more bound water, more calcium hydroxide consumption, or more strength, you have more reaction. There's various types of this, but typically the R3, the modified R3, and the lime strength have shown a lot of promise. The R3 test shows very good correlation with strength. It has significant potential for standardization. When it comes to specification, the bound water has a lot of promise. And what we have proposed is using heat release and calcium hydroxide consumption together, which helps differentiate inert pozzolanic and latent hydraulic material. And finally, the modified R3 test shows very promising results for several alternative SCMs. So thank you very much for your time, and that's the end of my presentation.
Thank you very much, Prannoy. Thank you very much. I have a lot of questions coming in, so I don't know how many we can take, but maybe later you can look at the chat also. So let me start with some of them. One question was, can SCMs become inert with time?
So I'm not exactly sure I understand that question, but if you have an SCM and you don't put it in concrete, the SCM is going to be reactive. It is unlikely that it becomes inert with time, because typically what is reactive is the amorphous portion. So that is going to continue being reactive. What can happen in rare cases is when you have a reactive fly ash and you expose it to moisture over a very prolonged duration, it will react and then it will harden. So that's not exactly inert, it's just that it's reacted. So this is typically not a major concern.
Okay. Any comments about metakaolin?
Yeah, so we have tested 2 or 3 metakaolins. Metakaolins are incredibly reactive, and actually, I think I had it on my slide with the R3. They are probably on the top of the heat that you get, so 900 or something like that. So yeah, metakaolins are a great material, as several of you can comment, and the ones that we've tested have performed very well.
And a question about fine GGBS, because in some places we have GGBS being ground and only the fine fraction being used. So there's a question, how do you think this compares with silica fume, metakaolin, and so on?
This is a great question. We've actually tested, I believe, well, I can't say the name, but it was an Indian GGBS, which was very fine. And in the different slags that we tested, we could clearly see that there were some slags which were performing significantly better than the other slags. And with those very fine GGBS, you could actually use it at lower replacements, or you could use it similar to a calcined clay or a silica fume. So that's a very promising material, in my opinion.
Okay, well, let's see. I'll stretch a little bit and ask some more questions. Someone had a doubt on what do you call reclaimed fly ash, or what is reclaimed fly ash?
Okay, that's a great question. So basically what has happened over the long term in the US is a lot of time there was no demand for a fly ash, or locally there was no use for that fly ash. So people pond and landfill flashes, right? Very roughly, you put that into the ground. Now what is happening is a lot of flash companies, power companies are closing down. So there is a need to get these flashes back. So you reclaim these flashes basically by getting them out of these ponds and landfills. And I don't have the exact estimates in mind, but they're about, I think, 700 to 1,000 million tons, if not more, of such material in the US.
Okay. Then one question from Ms. Dr. Rajamane, who has always been a very interesting, very important part of all our discussions. So he asks, due to decide between the rapid migration test and the bulk resistivity test.
So, well, okay, that's a great question. And it's a little complicated for me to answer to get out of the scope of this presentation. So the bulk resistivity is a very simple test compared to any sort of a rapid migration test, but you must be very careful with the bulk resistivity. So it is possible, if you do the bulk resistivity test wrong, that you can get completely nonsensical results. And the reason for that is the bulk resistivity in concrete is very strongly affected by the pore solution bulk resistivity. So there is a correction for this, which involves kind of accounting for the pore solution. If you do that, in my opinion, it's exactly as good as RCPT or as a migration test. But careless use of the bulk resistivity can give poor results. So it's a great test. It's very simple to do, but the interpretation is quite complicated.
Okay. Then I'll just give you one last question. How about impurities? How important are the impurities, or how disadvantages could the impurities of all these materials be?
I'm not sure what impurities means. Is it okay?
Like carbon and fly ash, some other. Like, how careful do you have to be that all these materials you talked about are really pure?
Okay, that's a very good question again. So, in order to use SCMs, one of the most important things is consistency. Even if you have a material which is perfect as an SCM, if one day the carbon, for example, one day it's 1% and the next day it's 3%, that's not a material that you can use. So consistency is something that's very important, and standards and specifications test for that. This is not a test that can do that. Now, with impurities, for example, things like carbon, or a great example would be alkalis or phosphorus pentoxide. These are materials which in very small amounts can completely mess up the reaction of the cement. So this test, the R3 or the modified R3 test, will not necessarily tell you that. It will tell you that the material is a good SCM, but you actually need to put it in concrete and verify that there are no negative effects because of things like impurities, etc. So that's a great question.
Okay. Thank you, Prannoy. If you go through the chat, you will see a lot more questions, and your presentation really kicked things up, and we crossed about 600 views. So yeah, people are really very interested, and a lot of questions have come in. So please see, if you have time, you can go through the chat and give some more answers.
Thank you very much, Professor Gettu. I really appreciate it. Thank you.
Thank you, Prannoy.